Welcome back to Physics 141 Online. Today I'd like to go through an overview of a topic called the kinetic theory of gases, where we see that a very simple model used to try to represent a gas of molecules inside a container, along with Newton's second law, can give us a profound insight into what's going on in a system like this. And it actually gives us a fundamental atomic level understanding of the meaning of temperature. So here's how the model starts. There's a cubic container that has a volume V and has N molecules in it. Each of them is identical with a mass V and a speed or velocity, with a mass m and velocity v. So you can see one of these molecules, which could also be an atom for a certain kind of gas, shown inside the container. And the direction of its velocity vector is some arbitrary direction, and what we're going to be concerned with for the purpose of this model is just to think about the x component of its velocity vector. So you'll see the standard coordinate system x, y, and z shown with the corner of the box at the origin. So what we're going to ultimately try to figure out is what is the force that these molecules exert on the walls of the container. So we will think about one of the sides of this container on the right hand side, and we want to ask ourselves how many, on average, how many of these molecules will collide with the right hand wall of the container in a time delta t. Alright, so the way we do this, it might seem like that's a very hard question to answer, but we realize, okay, if there's a molecule that's going to collide with the right hand wall in a time delta t, it has to have its x component of velocity is vx, and so it has to be within a distance vx delta t of the right hand wall, right? Because only those that are within that region will then strike the right hand wall within a time delta t, because vx delta t is the distance from the wall out to a certain point, and only those molecules within that volume will strike it. So only half of those molecules have an x component of velocity that's positive. All right, the ones that may have a magnitude vx large enough to strike the wall, some of them, roughly half of them, are also moving in the opposite direction. And so all we have to do then to estimate this number is to take 1/2 times the volume density of the number of particles in the whole gas, which is number of particles n, divided by the total volume v, and then multiply by the volume of this region close to the right hand wall. And that region close to the right hand wall has a length vx delta t, and then it's got a cross-sectional area a, because a is the cross-sectional area of the right hand wall, right? So what we've really done is we've taken this volume here multiplied by the number of particles per unit volume in the whole container, and then multiplied by half. And so if you think about the units, this gives us the number of particles that are in this smaller volume on the right hand side, and those are the number that are going to hit the wall. And again, the factor of 1/2 just accounts for the fact that only half of them have a positive x component of velocity. Now, why do we need that number? As we go on to the next slide, you'll see why. So each molecule colliding with the right hand wall will rebound elastically. And we can get a pretty good idea of why these collisions have to be elastic, because if they were not, if those particles were striking the wall of the container and then losing energy and bouncing back with a lower energy, then as they collided with the walls of the container over and over again, their energy would get less and less and less. And what would happen in practice then is that the volume of the container would shrink, because it's those collisions the particles make with the walls of the container that apply the outward force that keeps the container at that particular volume. All right, so when we have a balloon and we've got molecules of gas inside the balloon volume, at least over a relatively stable period of time, doesn't shrink, because those particles inside, when they collide with the walls of the container, bounce back with the same energy. So what we can do then for a single molecule is we can calculate the change in the x component of momentum that it has whenever it makes a collision. That's really easy because it moves to the right initially with a momentum mvx, and it rebounds going to the left with a momentum negative mvx. So the change in momentum, the final minus the initial, is minus 2m vx. The 2 is because it started off moving to the right, it came back moving to the left, and the minus sign reflects the change in the direction of the momentum. All right? That's for a single particle. Now we can estimate what this momentum change is for all the particles that collide with the wall during that time delta t, because we've already calculated how many of them there are. So we take the number that was calculated on the previous slide, multiply by this delta px, and that gives us the overall change in the momentum of all the gas molecules that strike the right-hand wall in a time delta t. So delta px is equal to, right, this momentum change for a single molecule times the number of molecules that make those collisions, and here's what we get as a result. We get a Vx squared term. Now, what we then want to do is change this quantity from a momentum change to a force. And one of the ways that Newton's second law can be written is in terms of change in momentum over change in time. So the force that is being exerted on these molecules when they collide with the walls of the container is their change in momentum divided by the time it takes for the collision. So we take this delta px term here and then divide by delta t, which means the delta t will cancel out, and it leaves behind everything else there except for the delta t. So now we've got something really interesting. Now we've used Newton's second law to figure out the net force that these molecules feel when they collide with the walls of the container. Now, there's a minus sign there because when they collide with the right-hand wall, then they end up moving to the left. So the force on the molecules has been exerted in the direction to the left. The force that we want for the purpose of this exercise is the force that the container wall feels, that those molecules exert on the container wall. And that's the same force that the wall exerts on the molecules, but just with a minus sign. All right? So what we have is the expression from the previous slide for the force on the wall. And we'll plug that in just a moment. The pressure then, the pressure which is the property of the gas that measures the force of the molecules per unit area of the surface that they strike, that's just the net force on the wall divided by its area. And if we go back, I'll just go back for a second, that force expression, this is what we're using down here, and so all we're doing is taking this, apart from the minus sign, and dividing by the A, and that gives us the pressure. So that's what we have right here. Now it's a little bit odd that we have this only in terms of the x component of the velocity, and so there's a way that we can change this equation so instead of just referring to the x component, we can write this in terms of the speed. And there's a symmetry argument that we're going to make in just a minute. So first of all, this would only be for those molecules that have this particular x component of velocity. What we need to do really to have a more accurate expression for the pressure is take an average over all of the molecules, because some of them, even though they will strike the container in that time delta t, they will have a speed a little bit less than this Vx, and some will have a speed a little bit greater. So let's take the average of the square of the speed. And you can see why that's necessary. We don't take the average of Vx and then square it, because Vx values can be positive and negative. And if we took the average of all those values, we would get 0. But if we have the square of those values, those are always positive. So we'll take the average of the square of the Vx squared value, the average of the square of the Vx values. So this gives us a more accurate expression for the pressure that the molecules exert on the walls of the container. And there's nothing special about our discussion that would tell us that the x direction is any different than the y or the z direction. So if we were to look at these quantities, the Vx squared average, the Vy squared average, and the Vz squared average, we would expect all three of those to be the same, because there's no reason that one of those directions is different than any of the other directions. Of course, we're neglecting the influence of gravity on these molecules because they have such small masses. So with this equality for the average values, then what we could do is write down an expression for the average of the square of the speed of the molecules. And of course, using our Pythagorean relation, v squared is vx squared plus vy squared plus vz squared, and that also applies to their average values as well. And here's the key. Since we've already reasoned that vx, vy, and vz squared values on average are the same, then instead of summing those three up, we can write that as 3 times one of them. And since we already have our original expression in terms of the vx squared values, we'll do that. So now I have a relationship between vx squared average and v squared average. So I'll solve this for vx squared average, right? That's easy. Just divide both sides by 3. And I see now I can take this vx squared average, which was in my pressure equation, and replace it with 1/3 the average of the v squared values. And this is nice because now I'm not having to distinguish between x or y or z components of the velocity vector, and I can just write down the average speed. So this expression for the pressure tells me that the pressure that the gas exerts on the walls of its container is equal to the number of particles times their mass times the average of the square of their speeds divided by 3 times the volume of the container. So if I simply take this previous expression, multiply both sides by v, I get P times V is equal to everything else that's left on the right-hand side. And if you remember the ideal gas law, this should look familiar, because one way to write down the ideal gas law was PV equals N times K, Boltzmann's constant, times the temperature. So let's compare this equation, which we've gotten just by using Newton's laws and our simple model of what's called the kinetic theory of gases. We see that PV equals NKT. That was an experimental relationship that was worked out by scientists over the course of hundreds of years. If we set that equal to the expression that we got based on our model and Newton's laws, we see that the n's are both present there, so they will cancel out. But what it allows us to do is solve for this v squared average term. And v squared average then, for all of these molecules in the gas, is 3 times Boltzmann's constant times the temperature over the mass. And if I just take the square root of both sides of this, I get a special sort of velocity value. And it's the square root of the average of the squares of the speeds. And so for this reason, we often, when we have a quantity like this, we often call this the root mean square value. And you may have heard of this before. It's a particular kind of velocity that reflects the fact that we've taken the square root of the average or the mean of the squared values of a particular variable, like this velocity variable. And the VRMS then is, it's not exactly the average value of the speeds, but it is a value that tells us a typical value for the speeds of the molecules in our gas when that gas is at a temperature T. And one question that we can ask, and you've got at least one homework problem that asks you to do this, is how fast is this? For a particular gas molecule at a particular temperature, what would we expect this to be? Is this going to be 10 meters per second, or 100 meters per second, or 1,000,000 meters per second? What kind of value should we expect for this? And we can plug in, as a very simple example, diatomic oxygen, which is the oxygen gas that we breathe in at room temperature of 300 Kelvin. So the molecular mass in kilograms, which is what we need to plug into the previous equation, we use the mass of a single atom of oxygen, which is 16 times 10 to the minus 3 kilograms per mole. It's 16 grams per mole, but we'll write down in terms of kilograms. There's a factor of 2 because oxygen, molecular oxygen, is O2, and we divide by Avogadro's number, which tells us how many molecules there are in a mole. And so if you look at the units, the reason we divide by Avogadro's number is we would like to know how many kilograms there are per molecule. In other words, what's the mass of a single molecule? And when you do this, you get a very small value, 5.32 times 10 to the minus 26 kilograms per molecule. So that's the mass of a single oxygen molecule. Now we go back to our root mean square velocity formula. We plug in Boltzmann's constant, which we know. We plug in the temperature of 300 Kelvin. In this expression, temperature has to be inserted in absolute units, in Kelvin units, and divide by the mass. So when we do that, 3 times 1.38 10 to the minus 23 joules per Kelvin, 300 Kelvin, the appropriate mass, and we get 483 meters per second. So a value for a typical atom or molecule at a temperature near room temperature is on the order of several hundred meters per second. And that, of course, if you look at the formula, will depend on the mass of the molecule and the temperature of the system. Generally speaking, at a particular temperature then, lighter molecules have higher speeds. So let's go back. Here, I'll just flip back to the previous slide for a second. What we want to do with this expression here, though, is interpret it not just thinking about how fast the molecules are moving, but what really does temperature mean? And so what I'll do here is cross-multiply in this equation. And going back to here, all right, there's our equation. Now, if I multiply both sides by m, and then I realize I've got m times this average v squared value, so then if I multiply both sides by 1/2, I get 1/2 m times v squared average, and that's equal to 3/2 Boltzmann's constant times the temperature. And you know what this represents? It represents the average kinetic energy of a single gas molecule, because it's 1/2 m times the average of the square of the speed, which we know is the kinetic energy. And so for the entire sample of n molecules, what we have here is an average value, averaged over all n of them. So if we multiply by n, this gives us the total kinetic energy, and I'll call it the translational kinetic energy because there's other kinds of kinetic energy that we could have, but it's the translational kinetic energy of the entire sample of molecules in the gas. We can write it as nk times the temperature, or little n times r times the temperature. And you remember that little n is the number of moles, while capital N is the number of molecules. Either one of these expressions is fine. They're equivalent to each other. So what this really tells us, if we go back to the upper right-hand equation here, it tells us what temperature means at the molecular scale. Temperature, then, is really a measure of molecular kinetic energies. So the temperature of the system would give us, through this very simple formula, the average kinetic energy of all of the gas molecules in the system. So we will use this formula when we get to the next chapter and we start to think about the way that gases can do work on systems. We can actually design engines that involve the compression and expansion of gases. When we do that, it'll be important to understand how to write down the internal energy of the gas molecules. And this translational kinetic energy is an important part to that. But for now, the take-home lesson is that this kinetic theory of gases gives us a fundamental understanding of what temperature means. And this was achieved in the late 1800s for the first time. And rather than then just thinking of temperature as sort of a convenient measure of what kinds of systems would be more likely to give up heat, now we understand that that temperature on the Kelvin scale connects directly to a property of the atoms and molecules that make up the gas. I hope that's a helpful introduction. Make sure to read this section in your book as well, and I will see you in class.